So we have looked at models already in great detail, including scenarios, but I like to include podcasts again because let's say this section on physical oceanography and climate is all you want to go through, then I want that to be as faithful to the book I'm using as possible to cover all the points that the book covers. So to some extent I'm repeating these things from different perspectives that different books use to cover the material or the flow of material. No harm done, because then you can just use this part for your edification, or you can learn the same thing in other parts as well. Okay, so typically when we want to look at how climate has varied in the past, we used some proxies, delta O18, delta C13, and various other isotopes and evidences and ice cores and sediments, tree rings, corals, etc. to estimate global mean temperatures, sea levels, and so on and so forth. But when you want to construct full circulation, distribution of rainfall, how El Nino has behaved in the past, and so on, you tend to rely on models, especially to project into the future. So we want to see where we are headed with this uncontrolled increases in greenhouse gases and our impact on land use changes and so on. So we have talked about models in great detail. There are governing equations which look at Newton's law of motion, so F equals ma for longitudinal circulation, latitudinal circulation, water vapor and moisture dynamics on how it produces the rainfall patterns and how energy is being moved within the system, and so on and so forth. So very briefly, this is the way Chris Karnauskas sees the structure of a model. So anatomy of a general circulation model as a coupled model, including component models representing the global atmosphere, so atmospheric GCM, and global ocean, so ocean general circulation model. GCM is a buzz acronym, so AGCM, OGCM, and CGCM correspond to various levels of complications or complexities, and other components such as ice, land ice, sea ice, and terrestrial and or marine biosphere, carbon cycle, and so on. The component models discretize their global realm with finite sized grid cells whose size is a function of model resolution. In other words, the equations that the governing equations are non-linear. They cannot be solved with paper and pencil. They have to be integrated numerically, which requires that we discretize it, use numerical methods, and so on, that we talked about in detail in the ocean, in the climate modeling part of this entire course that you can look up. So you need higher resolution to capture some of the processes, but then it increases the computational cost and so on and so forth. Grid cells must communicate with each other, so transparent arrows are shown here, while a coupler serves to exchange information between the component models. So the ocean serves water and energy to the atmosphere. Atmosphere drags the ocean around or cools and warms it, but with winds and heat fluxes and freshwater fluxes and so on. Typical prescriptions during the coupled general circulation model experiments include solar radiation at the top of the atmosphere and the concentration of greenhouse gases. So the amazing thing about models is that just given the energy that's coming in at the top of the atmosphere and some indication of how much greenhouse gases are present, the models are able to produce the trade winds, the mid-latitude westerlies, the Hadley cell, Walker cell, monsoons, El Ninos, and the alphabet soup of climate modes we saw, like the annular modes and the Pacific decadal oscillation and so on. But the models are not perfect. They tend to have a little bit of uncertainties and biases for various reasons. So here is the atmospheric general circulation model with its discretization, with, let's say, prescribed greenhouse gases, and each grid cell is here, which is exchanging temperature, heat, energy, momentum, and water vapor, and so on between boxes. And it is coupled to the ocean, which itself is also exchanging salt, heat, momentum, and so on, and circulating and creating all the ocean circulation, deep water formation, wind-driven circulation, and so on and so forth. So they are incredibly useful tools. Of course, only the atmospheric model tends to be used for making short-term weather forecasts, because on short time scales of a few days, the ocean doesn't change much. It's heavy, it's got high heat capacity, so you can consider that it's not changing very fast. But if you want to look at multiple weeks and seasons, then ocean begins to control how the atmosphere evolves. So we have coupled general circulation models for doing climate forecasts or predictions. And when we want to make projections into the future, you also want to prescribe how greenhouse gases will evolve, how population will evolve, how much energy we will use, what kind of transportation, land use, and so on and so forth, that we put into what are called narratives or scenarios that we'll come back and look at. So one of the main things that our models can help us with are called detection and attributions. We already mentioned this once, and here is a nice way to look at it, and we have looked at it in the earlier part of the course as well. So natural and anthropogenic forcings, various versions of the coupled models used in the previous IPCC assessment report. CMIP-3 was released in 2007 with one set of models at that time. The models are constantly being upgraded, improved, complexity is being increased, realism is being increased, and so on. CMIP-5 gave rise to the assessment report 5, released in 2014, and right now we are getting the release of assessment report 6 in what is called CMIP-6. So you can see that the observed data is here in the black line, and these various colors and the thick red and blue lines are from CMIP-3 and CMIP-6. So you can see that in general you use a large number of models, and the models are able to cover the evolution of temperature anomalies in the global mean over the 20th century, or since the Industrial Revolution into the 2020s, 2014 or so. Realistically, there are lots of differences that we will need some details to understand, which we are not going to go into in this very introductory course. So what does this mean? That means that we have detected a change in temperature in the 20th century, and we are convinced that the models are able to reproduce these changes, and then what we can do is to see if the detected signal can be attributed to human causes, or whether they are purely because of internal variability like El Nino and La Nina and so on. So the way they are done is that you make simulations like this with all the forcings of volcanoes, aerosols, greenhouse gases, solar activity like sunspots, and so on, and make sure that the models are capable of doing that. And then you run the same models by taking out the greenhouse gases to say, if human beings were not emitting the greenhouse gases, where would we be in terms of the global mean temperature? Okay, so you can see that when you remove the greenhouse gas forcing from the human activity, including the land use and so on, we wouldn't have this warming. This is the observed warming. In a counterfactual world where human beings were not emitting greenhouse gases, we would have been here. This is attribution. It means that this much of warming here since the 1970s or so is directly related to contributions of human beings to energy balance. The radiative forcing that we mentioned before is essentially this. It is trapping more energy, and it is increasing the global mean temperatures because of that additional energy. Okay, so that's a quick look at detection and attribution. So what we do for the future, of course, is create what are called narratives or scenarios, where you look at how the CO2 concentrations will increase, so net CO2 emissions starting from, let's say, 2020 going into the future, and you also combine them with how society will respond, whether it will opt for sustainability, whether it will opt for middle of the road, or it will not care about inequality, whether there will be regional rivalries, whether we will opt for rapid growth without worrying about climate change, and what kind of additional energy trapping will happen, starting from 2.6 watts per meter squared by 2100 to something like 6 watts per meter squared, or what is called baseline, which is about 8.5 watts per meter squared additional energy being trapped if we don't do anything or go as we are now. Of course, you can see that we have been increasing CO2 quite rapidly, as we already saw, and associated with there are mitigation challenges which can be high if we choose these socio-economic pathways. These are called shared socio-economic pathways, and the earlier pathways were called representative concentration pathways. So you can read up more, or you can leave it at that. So when the mitigation challenges are low, we have opted for sustainability and these pathways here, inequality, and adaptation challenges tend to be low in this direction, or they can be high in this direction, and the resulting warmings are shown here. So you can be in the range of 6 degrees, 5 degrees, or 4 degrees global mean temperatures, and if you want to remain safe and restrict yourself to less than 2 degrees C warming global mean with some 67% probability by 2100, then you can see that you have to start reducing the net CO2 emissions and even have negative emissions, which means we take out more CO2 from the atmosphere and other greenhouse gases than we emit. So there are some emissions that are unavoidable, but we will have carbon capture and sequestration and bioenergy and so on that will actually end up in net negative emissions, so that we can remain within what we consider safe global warming targets, like less than 2 degrees C by 2100 with certain probabilities. Okay, so here is the future projections of global mean sea level from doing all this, which I won't go into details, but I will do it in the next podcast, because that begins to get into the ocean's role. So if ocean is taking up most of this heat that we are creating by additional trapping of energy because of increasing greenhouse gases, then ocean is going to expand and sea level is going to rise. This is a huge challenge for many coastal cities, low-lying islands, and so on and so forth. So we have to worry about those things when we worry about ocean's role in climate change. Okay, so let's come back and look at that in the next podcast.